Hi students, in our previous video we had discussed about the cleavage of carbon-oxygen bond in ethers. We are still continuing with the same topic about the cleavage of carbon-oxygen bond, in ethers. Today we are going to take some examples on the carbon-oxygen bond cleavage for the ethers. So let us take the ethers. We had already discussed that ROR, when reacted with any hydrogen halide, there is going to be the product that is called Rx, and also the hydrogen is going to be attached by one of the ROH group. The alkyl halide is our major product. That is the yesterday's topic we had discussed. Now let us take one example. We are using a substituted ether. We are using a substituted ether. We had already got about the substituted ethers in the previous class. Means you can observe CH3OC. The carbon is having two substitutions and we had already given the naming. Now we are seeing this one as a substituted ether. What will be the product, or on which side of the alkyl group? On which side of the alkyl group? Less substituted or more substituted will involve in the carbon-oxygen cleavage here. When it is treated with a hydrogen halide, I am using hydrogen bromide. Okay. There are two conditions here. The carbon-oxygen bond may be cleaved on the carbon having more substitution, or the carbon-oxygen bond can be cleaved on the side where the carbon is having less substitution. Now let us see here, if at all we observe the carbon-oxygen bond cleavage is taking place between the carbon with less substituted side, then what will be the product? The product that we expect is CH3O, CH3, CH3. For this part, we get the hydrogen bonded and the remaining will be CH3Br. This is what we expect. In this course of reaction, that is the mechanism, it is going to form an intermediate that is called primary carbocation. This will be formed by the formation of primary carbocation as a reaction intermediate. Now let us take the chance, if at all the carbon-oxygen bond is going to be cleaved at the highly substituted carbon, then we write this reaction as CH3 plus HBr. Now our task is, this is the highly substituted carbon. If the cleavage takes place at this location, it is going to form a bond with bromine, that is CH3, C, CH3, CH3 and Br. As usual, it will form the remaining CH3OH. Among these two, which will be formed? Means when we study the intermediates that are formed in the reactions, in this case, it will form through an intermediate called primary carbocation. How do we say this? This is an negative nucleophile, so this will be an electrophile. The electrophile is the intermediate. We are not showing the reaction in intermediates now. Among tertiary carbocation and primary carbocation, which will be more stable? Yes, tertiary carbocation will be more stable than the primary carbocation that we had learned in the first year. So which will be the product that will be formed when substituted ether is reacted by the hydrogen bromide? The product will be the one in which the carbon oxygen cleavage takes place at a highly substituted carbon, because it is forming a stable tertiary carbocation. So this is the product that will be formed, but not this. The reason is, when the reaction is going on, the intermediates when we study, that is going to form a stable tertiary carbocation. So that is the product that takes place in the substituted ethers. We have discussed only the ethers that are having only the alkyl groups. What groups are we having now? Only alkyl groups. Now let us take another example in which the ether will have an alkyl group and also an aryl group. So let us continue the cleavage of carbon oxygen bond in alkyl aryl ethers. What kind of ethers we are discussing now? Alkyl aryl ethers. In this type, there is an alkyl group that is represented with the R, and the aryl, that is the benzene. These both are having an ether linkage. These type of ethers we call as the alkyl aryl ethers. Now let us remember the main point. In this case of alkyl group, I am going to take a simplest alkyl group, that is called CH3. What is it called as the CH3? Now observe the hybridization of the carbon in the case of alkyl group. In the case of the alkyl group, the carbon is going to exhibit sp3 hybridization. Which type of hybridization is going to show? sp3 hybridization. The alkyl carbon is going to show sp3 hybridization. But on the another side of the either bonding, there is oxygen, we got one more carbon on the benzene. This carbon on benzene, it got a double bond with another carbon. So what kind of hybridization we observe on the carbon of benzene? Carbon of the aryl, that is the benzene, shows what kind of hybridization? Double bond, whenever it is present, it is going to show sp2 hybridization. What kind of hybridization is going to show? sp2 hybridization. So first we must be very clear with the kinds of hybridizations that are exhibited by the carbon atoms. Alkyl group is showing sp3 hybridization, and the carbon of the aryl group is showing sp2 hybridization. Now the topic is cleavage of carbon oxygen bond. The carbon oxygen, here the carbon oxygen, which bond will be cleaved readily is our concept. The bond which have less electronegativity, or we can speak in the case of sp3 hybridization and sp2 hybridization. The lone pairs on the oxygen are readily involved in conjugation with the benzene ring. In the case of sp2 hybridization carbon, the lone pairs are readily involved in conjugation with the benzene ring. But the lone pairs are not involved in conjugation with the sp3 hybridized carbon of the alkyl group. So here length decreases. What happens? The bond length decreases between the sp3 hybridized carbon and the oxygen due to the involvement of lone pairs in the resonating structures. So this bond will not be cleaved or break. Which bond will not be cleaved or break? Carbon-oxygen bond of the aryl group will not be breaked due to the involvement of lone pairs with the benzene ring in the resonance. But the alkyl group which is having sp3 hybridized carbon is not involved in resonance, so it is easy to break the methyl group bond with the oxygen. How does this cleavage take place? The cleavage takes place in the presence of a hydrogen halide. The cleavage takes place in the presence of an hydrogen halide. I am going to call this one as the hydrogen bromide. What is this one called as the hydrogen bromide? Here, what is the name we can give? Shall we call this one as anisole? What do we call this one as the anisole? Anisole, when reacted with hydrogen bromide, there is a bond cleavage between the oxygen and methyl group, and here comes with the hydrogen substituting the alkyl group, because oxygen will have a negative charge once it has withdrawn the bond towards it. The negatively charged oxygen will give the electrons for the electrophile. Which is the electrophile here? Expresses the electrophile. So, negatively charged oxygen will give electrons for the electrophile, forming OH, and here the methyl will form CH3Br. So, what is the product we are going to get? We are going to get the product phenol and bromomethane. So remember children, why does the carbon cleavage takes place only in the alkyl side? Because the oxygen lone pairs are not involved in the conjugation. But here we have aryl group, oxygen lone pairs are involved in conjugation with benzene ring that decreases the bond length, hence its bond will not be cleaved. So whenever we react anisole with hydrogen bromide, what is the product we get? We get phenol and bromomethane. So this is the topic that we have discussed under the chemical properties about the cleavage of carbon-oxygen bond in the alkyl aryl ethers. Let's take the second chemical property. Let us see the second chemical property about the electrophilic aromatic substitution reactions. We have discussed up to now carbon-oxygen bond cleavage as the first chemical property. Now we are taking the second chemical property as the electrophilic aromatic substitution reactions. Aromatic, whenever you get the word, you must remember that an aromatic compound is present in the given reactant. That will be compulsory a minimum benzene ring that we use in our general reactions. So the benzene ring containing ethers, we have one of the benzene, that is aryl group, and also another part is the alkyl in our ether. So we call this one as the alkyl aryl ether. Alkyl aryl ether. What kind of chemical reactions are they involved? Means they are involved in the electrophilic aromatic substitution reaction. We have taken one example in the previous case. What is the example we have taken in the previous case? OCH3. What is the name we had given? Anisole. Now let us study the nature of the substituents. We know phenyl is an electron withdrawing group, but this methyl makes the plus I effect. Which effect it is going to give? going to give the plus I, Fn is going to deal with the electrons and is making the oxygen to involve its lone pairs in conjugation with the benzene ring. So this entire methoxy group we can call, it is favoring the benzene to the oxygen to delocalize the electrons on the benzene. So can you observe the electrons will be shifted onto the benzene. Here what do we observe? We observe it is going to be forming an negative charge on the ortho position. Which position? Ortho position. Means shall we call on the ortho position, it is acting like a nucleophile. It is acting like a nucleophile. Don't forget that here there will be one hydrogen. Here there will be one hydrogen. So this nucleophile will try to give the electrons for an electrophile. Electrophiles are the electron diffusion centers. Once that center is getting bonded here, the hydrogen bond cleavage takes place. Means the hydrogen will be left as another electrophile. So at this location, one electrophile will enter and also another electrophile will be leaving the benzene. So this is called as an electrophilic aromatic substitution reaction. At what locations does the electrophilic aromatic substitution reaction takes place? It takes place wherever there is a negative charge on the benzene ring. Where do you find now? You are finding only at ortho, but still this is involved in resonance. This is involved in the resonance. I am hiding the oxygen, hydrogen. When it comes in resonating structure, it will be forming a negative charge at the para position. A negative charge at the para position. This is the para position. It is further involved in the resonance so that we find the negative charge still at the ortho position. At last, the negative charge will be retained back on the oxygen. These are the resonating structures of anisole. During all these resonating structures, where do we find nucleophilic centers? We find nucleophilic centers at the ortho, para and ortho dash. So at these locations, the electrophile can be substituted. This one electrophile will be entering and one hydrogen from these locations will be removed. So what do we say is the electrophilic aromatic substitution reactions in the alkyl aryl ethers takes place at ortho, para and the ortho dash. Let us see the examples here. So let us take the explanations for the electrophilic aromatic substitutions. And we have our first example, that is called bromination of anisole. What is the formula of anisole? You know, benzene OCH3 is called as the anisole. Bromination means we are going to add bromine here. Please observe the reagent. Another reagent is acetic acid, or we call it as the ethanoic acid. So when the bromine is going to be added in the presence of ethanoic acid on the anisole, the Br plus will be generated in this reaction. Br plus. Shall we call this one as an electrophile? We are not seeing a mechanism here. We are observing what is generated. It is generated as the electrophile. At what locations does this electrophile will be added? We already came to know the anisole CH3 group is a ring activating group that it favors for negative charges at ortho, para and ortho dash on the benzene. So the electrophilic substitution takes place at ortho, para or ortho dash. Here the mono substitution takes place. Which substitution takes place? Mono substitution takes place. Means any one product will be measured. Please observe, when anisole is reacted with bromine and ethanoic acid, it is going to form a mono substitution. Means one bromine will be added onto the benzene ring. Please observe, children. Here I have used one anisole. So in the product I have mentioned one product. But if I increase 2 moles, how many anisoles will be there? 2 anisoles will be there. One anisole will be forming an ortho product. Shall we give a name? This one as ortho. What is this one called as the ortho bromo anisole. The name of the product is called ortho bromo anisole. And if you observe, we may get a para product also. What product also we can get? A para product also. Here bromine is a ortho meta para. So this is called para bromo anisole. We got 2 products here. Don't forget, from here one hydrogen will be removed in the form of H plus. And here we have another bromine. No? Those both they will be leaving in the form of HBr. How do they will be leaving in the form of the HBr? Means 2 molecules we are getting. So we can say they are in the form of 2 moles of hydrogen bromide. No need to balance the hydrogen bromide when we take the reactants. Now let us see among ortho bromo anisole and para bromo anisole. Please remember, Br2 in ethanoic acid. What is the electrophile generated? Br plus is generated. We will be getting any one as the major product. Get here, bromine is a halogen. It will have lone pairs, and this itself is a very bulky group. Bulky means very large group. These electrons that are present on the halogen and on the oxygen, they will experience the repulsive forces that makes the molecule unstable. Unstable means that will be the minor product in the reaction. What will be the minor product in the reaction? And another case when we see the halogen that is having lone pairs is far away from the oxygen that is having the lone pairs on anisole. So here repulsions are very less. Which repulsions? The electron lone pair repulsions on the oxygen and halogen are very less. When the repulsions are very less, they are going to form the stable product. Stable product means it is going to form the major product. So when we react anisole with bromine and ethanoic acid, Br plus will be an electrophile generated in the reaction, and it is undergoing a mono substitution. Among the 2 products, one is the major, that is para bromo anisole. That is the more amount, 90% of the product will be formed here. But the least is the minor product, that is called ortho bromo anisole. Byproducts are hydrogen bromide. Let us take the next example. Let us see the second chemical properties, that is the electrophilic aromatic substitution. In that, the second example, we have taken Friedel-Crafts alkylation. We had already discussed the Friedel-Crafts alkylation reactions in the first year. So the same, it comes like, let us take example now. Alkylation means our anisole is going to get an alkyl group as the electrophile in the reaction. Further, our anisole, we are going to react it. Anisole, we are going to react with CH3Cl. What do we call as the chloromethane? For this, take up the chlorine and it will form AlCl4 minus as one of the byproduct. Remaining part will be the CH3 plus. Shall we call this as the methyl carbocation? Is this an electron center or electron deficient center? This is an electron deficient center. Electron deficient centers are called electrophiles. What are they called as the electrophiles? So this electrophile that is generated when we had reacted CH3Cl with HCl3 is going to enter into the reaction. Now we already applied that anisole is going to form an ortho product and also an para product. What kind of product it is going to form? An ortho product and also a para product. Alkylation of anisole. Alkylation of anisole in presence of anhydrous AlCl3. Anhydrous AlCl3 is called Friedel-Crafts alkylation. What is this one called? Friedel-Crafts alkylation. Now, on which side the methyl groups are added? Ortho and also para. Now we have the time to give the naming. Here we have the methyl group as the primary one and it is going as a substitution. So we give the name 2-methoxytoluene. What is the name we give here? 2-methoxytoluene. And what is the other name we give here? 1, 2, 3, 4. 4-methoxytoluene. 4-methoxytoluene. What is toluene? Benzene CH3 group is called as the toluene. According to IUPAC, when giving the naming, the either group will give less priority than the alkyl group. So we started the numbering with the alkyl group on the benzene. Among these two, which is the major one? Here, the methyl groups which are bulky, they will have repulsive forces between each other. Hence, they will be forming less stable product. Means it is going to form an minor product. But the methyl and the methoxy, they are far away from each other. Means they are para to each other. Hence, they are going to form a stable intermediate. That is stable product. So they are going to form the major product. What product are they forming? The major product. So what is Friedel-Crafts alkylation? Reacting or alkylation of anisole in presence of anhydrous AlCl3 is called Friedel-Crafts alkylation. The same phenomena we take up now by heading Friedel-Crafts acylation. In the place of CH3Cl, they will take acetyl chloride. Let us take up the example. Let us take the next example. That is what we are giving, number B. Under the second and number B. Friedel-Crafts acylation. What reaction we are going to call? Friedel-Crafts acylation. Here previous is alkylation. At the time what we said? We had introduced an alkyl group. Here we are going to introduce an acyl group or acetyl group. We can also call. What is an acyl group or acetyl group? This group of atoms, that is CH3C double bonded O. This is called as an acyl or acetyl group. What is one called as the acyl or acetyl group. Now let us take the reagent CH3C double bonded O Cl. It is called chloride or ethanoyl chloride. Ethanoyl chloride. It is going to be added in the presence of anhydrous AlCl3. Anhydrous AlCl3. So this so-called acetyl chloride, when added in the presence of anhydrous AlCl3, the chlorine will be taken up by the electron deficient center aluminium, forming AlCl4 minus, and the remaining part is CH3 C double bonded O plus. So this is going to be our electrophile. Where do this electrophile will be added? In the case of anisole, electrophile will be added at the ortho or para positions. Let us see here the products that we come across. The products that we come across here are OCH3 is the anisole. Here we come across the COCH3, that is this COCH3 is bonded to the benzene, and the another product that we expect is OCH3 COCH3. Here, what is the name of the product we can call? Here this part is also called, when attached to a benzene, as the acetophenone. When it is attached to the benzene, it is called as the acetophenone. That is C double bonded O CH3 is called as the acetophenone. It is having highest priority than the ether group. So it is called, the product is called 2-methoxy acetophenone. 2-methoxy acetophenone. Another product is also called 1, 2, 3, 4. What is it called? 4-methoxy acetophenone. This 4-methoxy acetophenone will be the major product. You can understand why. Due to less repulsive forces. And here, acylation of anisole in presence of anhydrous AlCl3 is called Friedel-Crafts acylation. So these are the chemical properties of the alkyl halide ethers. By this we had completed the chapter number 11, that is called alcohols, phenols and ethers. Still there are some physical properties that we shall discuss later. Thank you.